Hello everyone, welcome to yet another math video. In this video, I'll be covering the Rational Zero Theorem, otherwise known as the Rational Root Theorem or the Rational Zeros Theorem. And if you are in a course I teach, this corresponds to section 3.4 for college algebra, and possibly a section in pre-calculus as well. In this video, I'm going to go over what the Rational Zero Theorem is, when you'll use it, and then we'll go through the preliminary things that you need to know about using the Rational Zero Theorem, how to find the list of possible zeros using the theorem, and then we'll do a bunch of examples, and then I will end with writing functions from zeros. Let's jump into it. What is the Rational Zero Theorem? The Rational Zero Theorem, as you can see, is here. And there's a lot of jargon going on here. The Rational Zero Theorem states that if the polynomial f of x equals a sub n x to the n power plus a sub n minus 1 x to the n minus 1 power plus all this stuff, if it has integer coefficients, then every rational zero of f of x has the form p over q, where p is a factor of the constant term a sub 0 back here, and q is a factor of the leading coefficient a sub n, which is up here. When the leading coefficient is 1, the possible rational zeros are the factors of the constant term. Whoa, it's just much better understood when you see an example. But why is this a thing? Why is the Rational Zero Theorem something that exists? Why would you use it? In math, I have to be very specific with my wording. In math, it's used to find zeros of a polynomial that aren't solvable by any method that you've learned up until this point. So essentially, we're going to have functions that don't look like they can be factored. Factored is the big one. And we're not looking at quadratics anymore. We're looking at cubics. We're looking at quartics. That's x to the 4th power. We're looking at bigger polynomials where the quadratic formula will not work. So we want to be able to solve as many equations as we possibly can. We want to be able to find the zeros of functions, as many functions as we can. This Rational Zero Theorem is a tool to help us in that direction. How do you use this theorem? How does this theorem fit in the process of solving functions to find their rational zeros, or all the zeros? Let's take a look. All right, creating a list of possible zeros, I mentioned on the last slide, makes way more sense if you see it in context of an actual function and you can see what's going on. So we have this function, f of x equals 6x cubed minus 13x squared minus 41x to the first minus 12. And essentially what the Rational Zero Theorem tells you is you will take the factors of the constant here, and you will divide every factor of the constant term by every factor of the leading coefficient. So what does that look like? Well, just what I said. You have to find all the factors of 12. So it's basically asking what numbers divide 12 evenly. And there's a whole list of them that work, right? 1 divides 12, 2 divides 12, 3, 4, 6, and 12. All of these numbers divide 12 evenly. From there, you have to do the same thing for the denominator. The factors of 6 are 1, 2, 3, and 6. So how does this work? I realized on the last slide it said if you don't worry about, if your only factor in the denominator, or your only factor of the leading coefficient is 1, then the list is just what's in the numerator here, just the factors of the constant. So if the only number in the denominator was 1, you just get the list of factors out of the top, and that is your list of possible zeros. pretty straightforward. But since we have multiple factors here in the denominator, here's how you have to go about doing it. I'm going to first go through and divide every single number in the numerator by 1. And usually you start with 1, it's the easiest one to work with. So right now, I know my possible zeros list is going to be 1, 2, 3, 4, 6, and 12, and it's going to start here. All right, now I'm done dividing by 1. Next, I have to go through and divide every number in the numerator by 2. That being said, I only need to add the new numbers. So when I divide 1 by 2, that's 1/2. I look through my list, I don't have 1/2 yet, so I'm going to add 1/2. And then you just repeat this process over and over and over. 2 divided by 2 is 1, that's in my list. So I'm not going to write it again. 3 over 2 is not in my list, so I will write that. Let's see, that's 3 over 2. 4 over 2 is 2. That's already in my list. 6 over 2 is 3. That's already in my list. 12 over 2 is 6. That is also already in my list. So I'm done with 2. You go through and do it for 3. You'll notice you get 1/3 and 2/3. 3/3 is 1, that's in the list. 4/3, that's not in our list yet. 6 over 3 is 2, and 12 over 3 is 4, so that's in the list. We don't worry about that. So we're done with 3, and you just keep going down the list here. So 1 divided by 6 is not in my list, so 1/6. 2 divided by 6 is 1/3, there it is. 3 divided by 6 is 1/2. 4 divided by 6 is 2/3. 6 divided by 6 is 1, and 12 divided by 6 is 2. So the only one that we added here with this denominator 6 is the 1/6. All right, so how do you finish this up? You have to put some brackets around it and a plus or minus in front of all of this. At least that's how you would write it out on paper. And that's it. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 numbers in this list, but each of them can be positive or negative. And that's because you can evenly divide a 12 by, say, a -2. You'll just get a -6. So instead of writing all the plus and minuses here and here and really making this look scary AF, you just deal with the plus and minus at the end. Now, if you're working with some sort of online homework management system, MyMathLab, WebAssign, Schoology, all this stuff, you may have to go through and type out each zero separately. You may have to type it in 1, -1, 2, -2, 3, -3, so on and so on, all the way over until you get to 4/3, -4/3, 1/6, -1/6. And I assure you the order will not matter as you type these in. But that's how you create the list of possible zeros. And this right here is all the Rational Zero Theorem tells you. Just how to create this list right here. That's all it is. How do you create the list? Using that list, that theorem in a larger process is how we find all rational zeros of a function. Let's take a look. Using the theorem. Using the theorem is just one step in the entire process of finding all zeros of a function or all real zeros of a function. So it's the first step, which is nice. So you can use the Rational Zero Theorem to find a list of possible rational zeros for that function. The second step just ends up being synthetic division. You have to use synthetic division until you find a zero. That could take a few iterations to find a zero for that function. And I've got a couple hints to help you along the way with that. 3, you will repeat steps 1 and 2 until you have a quadratic result from the synthetic division. 4, you will solve that quadratic by factoring or using the quadratic formula, things that you already know how to do. And then 5, you have to give your answer. It depends on what the question is asking. Sometimes they'll ask for finding all real zeros, which means if you get any imaginary zeros, you will not include them in your list. Other times you will find all zeros, in which you would include all real and imaginary zeros in your list. So take a picture of the screen, take a screenshot, something. I'm going to be referring to these steps as I go through the examples over the next 4 slides. I hope they go relatively quickly for you guys. See you there. Okay, find all zeros for this function f of x. Now this, you may have noticed, is the function that I used a couple slides ago to create the list of possible rational zeros. The second step is to synthetically divide. And I can synthetically divide by what? Well, we have this list of numbers here with a plus or minus in front of it. And I don't know, you pick one. You pick one until you're lucky enough to find one that works. How do you do that? What do you suggest we do? Well, you will start with small. Remember, all of these numbers in this list have a positive and negative version. Positive numbers are generally easier to work with, so you want to start with positive numbers. And I would be willing to bet that the majority of people watching this would say that whole numbers are easier to work with than fractions. So you want to start with the small, positive whole numbers. So I'm thinking like 1, 2, 3, and 4. If you get to 4 and nothing works, maybe you try the negatives of those whole numbers. I'd rather work with negatives first before fractions myself. And then if you're finding those don't work, then you can just progress through this list as you see it. So step 2 can take a while, and it is just synthetic division. So I'm going to start with 1. I'm going to pick 1 from this list. I'm going to say x equals 1 when I divide. Just randomly pick it. What do I divide? We divide this function up here, 6x cubed minus 13x squared minus 41x minus 12. So we have the coefficients here, 6, negative 13, negative 41, negative 12. The last number of every synthetic division is going to be the remainder. So let's just run through it real quick. This is 6. 6 times 1 is 6. 13 plus 6 is negative 7. 1 times negative 7 is negative 7. I don't think this is going to work. Add these together, negative 48. 1 times negative 48 is negative 48. And 60. Sorry, negative 60 is our remainder. So here's the conclusion that we can draw from this. Remainder is not equal to 0, so x equals 1 is not a 0 for f of x. Now, you don't have to write this down, this whole explanation down, but that is what the remainder is telling you. So you'll go through and you'll try 2, and you'll try 3, and I'm going to try 4 because I have some insider knowledge here. So I'm going to keep doing synthetic division. I'm stuck on step 2 until I get a value here that gives me a remainder 0. And I'm guessing you've figured out by now that x equals 4. I pick it because it gives a 0. And no, don't cheat your way through this. This is 24. I'm sorry, that's 6, not 24. 4 times 6 is 24. This is 11. 4 times 11 is 44. 44 minus 41 is 3. 4 times 3 is 12. The remainder is 0. So this remainder equals 0, and that tells you x equals 4 is a 0 for f of x. So I'm going to have my answers up here in green. So I know x equals 4. That's just part of my answer. Already, I know. So how do you find the other answers? This cubic tells me I should have 3 answers. That's the largest exponent I have. I'm going to have 3 answers for this. There may be some multiplicity there, that's fine, but you're going to have 3 answers. All right. How do you do that? Well, you'll notice that this answer down here, 3 is 6x squared plus 11x plus 3 is quadratic. So we don't have to go through and repeat this process again. That's what the next example is. So what do? You solve this quadratic. What do you mean solve? It's not set equal to anything. You look right here, you just imagine there's an equal sign right here. It's equal to 0. Since we're trying to find zeros, we're going to set that quadratic equal to 0. So when you do that, you can solve by factoring, or you can solve by the quadratic formula. This factors, so I'm going to use factoring. This would be 3x, what is that, plus 1, 2x plus 3. There it goes, and that equals 0. And when you solve each of these for x, you'll get x equals negative 1/3, right? Subtract 1 and divide by 3. And here you'll get x equals negative 3 over 2. Subtract 3, divide by 2. These are also answers that go in our list. So I've got 4, negative 1/3, and negative 3/2. And some of you out there may be saying, ooh, I see it. Negative 1/3 is right here because there's a negative sign in front, and negative 3/2 is right here because there's a negative in front. It turns out that this is coincidence. You might be lulled into thinking after seeing one example, oh man, all of the zeros that I'm going to find for every single polynomial function I have are going to be in this list. No, that will not always be the case. Think about using a quadratic formula down here. If you had an answer that had square roots in it, there are no square roots in this list, and there never will be any square roots in this list that you create anyway. So the zeros you get here may or may not be in the list you created to begin with. Just a word of warning, don't look for your answers to be in this list. Let's take a look at what happens when you have to run through this process twice. All right, new example. We have used the rational zero theorem to find the zeros for f of x equals x to the 4th minus x squared minus 12. And yes, you can factor this, however, I'm using this example for multiple reasons. So we're going to use the rational zero theorem for this. First step, create a list of zeros. So 1, let's create a list of zeros. We need all of the factors of the constant term, 12. That seems to be a pretty common number right now. 1, 2, 3, 4, 6, and 12. All of the factors of the leading coefficient, 1. Now remember, when the leading coefficient is 1, your list is just the factors of the constant term, 3, 4, 6, and 12. So we can pick plus or minus 1, plus or minus 2, plus or minus 3, so on and so on. So let's pick 1. So we're starting with our synthetic division. 1, let's see, we have 1, 0, negative 1, 0, and negative 12. These zeros are here because when you're working through synthetic division, you have to represent every power of x between the degree and the constant. So x to the 4th, x to the 3rd, x squared, x to the 1st, and constant. So we try 1. Let's see here. Bring down the 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. 1 negative 1 plus 1 is 0. 1 times 0 is 0. That's 0. 1 times 0 is 0. That is negative 12. 1 is not a 0. All right, let's try 2. So 1, 0, negative 1, 0, negative 12. Bring down the 1, 1. 1 times 2 is 2, 2 plus 0 is 2, 2 times 2 is 4, that's 3, 3 times 2 is 6, that's 6, 2 times 6 is 12, okay. So 2 is a winner, 2 is a 0. Take a look at this answer down here. We have x cubed plus 2x squared plus 3x plus 6 equals 0. Ooh, okay, it's not quadratic. So what does that mean? That means we have to go through steps 1 and 2 again. So I'm going to go back to step 1 in a different color. The factors of the constant divided by the factors of the leading coefficient. Oh, cool. So the leading coefficient, again, is 1. So we can just have a list that looks like this. The factors of 6 are 1, 2, 3, and 6. So you go through again now with this polynomial down here and do synthetic divisions. I happen to know already the 0 we're looking for is going to be negative 2. So let's take a look at what happens when we use negative 2. We get 1, 2, 3, and 6. Bring down the 1, multiply by negative 2. Okay, that's 0. Negative 2 times 0 is negative 2. I'm sorry, it's not. It's 0. 3 plus 0 is 3. Negative 2 times 3 is negative 6. And 6 minus 6 is 0. So negative 2 is the winner. You don't know that going into it. You would try 1, you would try 2, maybe you would try 3, and then you would go back and start looking at negative numbers. But the short of it is negative 2 is one of our answers. So we have x squared plus 0x's plus 3 equals 0 now. Now there's something quadratic. I'm going to take care of this quadratic on the next slide. So here I am set up with everything from the last slide that we need. We have the last polynomial that we had after a synthetic division. It is quadratic, so we don't have to use synthetic division anymore. We don't have to create another list. I have the two zeros that we found to work, 2 and negative 2. Now we just have to solve this quadratic. And I mentioned earlier you can solve it by factoring or the quadratic formula, but this one presents the ease of the square root property. So let's use the square root property for this. We can subtract 3 from both sides to get x squared equals negative 3. You can take the square root of both sides with the plus or minus here. The square and the square root reduce away, leaving you with x equals this plus or minus the square root of negative 3. You can't have a negative inside the square root, so you have to bring it out front. And that leaves you with an I square root of 3. So here are the other two zeros for this function. So plus or minus I square root of 3. So the distinction I mentioned earlier, you may have to find all zeros, you may have to find all real zeros. That being said, this answer here is all. If it asked for all real, you include everything that is not imaginary. So all real zeros would look like this, x equals 2 and negative 2. So it just depends on what is being asked of you. Just make sure you're going through and reading the examples or the exercises carefully. And I want to take it back to the original function that we had, which you can see down here. The highest power on x, the highest exponent we have here is 4. Now I said in the first example, this is the number of answers you should expect. You should expect 4 zeros. And here they are. We've got 2, negative 2, positive I squared root of 3, and negative I squared root of 3. There are 4 answers there. So when I say this exponent represents how many zeros you have, What I mean is how many real and imaginary zeros you have. And one last thing I'm going to point out for right now is you'll notice that there are 2 imaginary zeros and 2 real zeros. More importantly, that there are 2 imaginary zeros. More on that later. On this slide, the last example for finding zeros. Here's the function. You want to create your list of zeros first, the list of possible rational zeros. Then you want to go through and do your synthetic divisions to actually find a zero. And once you do those 2 steps, come on back. In about 10 seconds, I will have a lot of work on the page. All right, so you find a list of zeros. You take all of the factors of the constant and you divide it by all of the factors of the leading coefficient. So what that looks like, 1 and 5 are the factors of the constant, 1 and 2 are the factors of the leading coefficient. Divide 1 and 5 by 1, you'll get 1 and 5. Divide 1 and 5 by 2, you get 1/2 and 5/2. Pretty straightforward. And lucky me, I picked -1 the first time around, and I was able to get a synthetic division with a remainder of 0. That being said, you cannot be afraid and you cannot get discouraged about this process. Chances are you won't pick the number or one of the numbers, one of the zeros, right off the bat. If you don't, that's when you double down. Say, okay, I'm going to find it. If you don't find it the second time, you don't give up. I'm going to find it. Third time, maybe you find it. Fourth time, maybe you find it. Don't give up. So I found a 0. I can go back and I can fill in these blanks, and I have a new polynomial. Well, it's not quadratic, so I have to do this process all over again. I have to find another list. I have a constant of 5, and I have a leading coefficient of 2. So guess what? My list is going to be exactly the same. So 1, 5, 1/2, and 5/2. So run through. I'm going to pause for some time. It'll go over to the next slide. Find the correct value here. That is 0 of this function. I'll give you a hint, and I'm not sorry about this. It's got to be a fraction. So try either 1/2 or 5/2 or -1/2 or -5/2. Let's see where this goes. Here it is. Positive 5/2 is what works here. Luckily, all these numbers in the denominator are even, so that makes this a very easy computation. When you bring down 2, 5/2 times 2, the 2's end up reducing away and just giving you 5. That's why this 5 is here. -3 plus 5 is 2. So the same thing happens when you multiply 5/2 times 2. You get another 5. -7 plus 5 is -2. Luckily, when you change this over here to a -2, it just changes to a -5, and you end up with a 0. So we have this particular function left over. It is quadratic, so we can use factoring, or we can use the quadratic formula if it doesn't factor. So I see right now that this does not factor. And since we're looking for, go back if you need to, the real zeros, we have to do the quadratic formula to see if this yields real zeros. Okay, so I know my A is 2, my B is 2, and my C is -2. So this is a negative B plus or minus the square root of B squared minus 4 times a times c, that's a negative 2, all over 2 times a. It's a lot of 2's. This is what the potential zeros equal. So let's see, inside the square root here, I've got a 4, and I've got a negative 4 times 2 times a negative 2, which is negative 16, or sorry, positive 16. 4 plus 16 is 20 in the square root. So negative 2 plus or minus 20 all over 4. We can simplify that. The square root of 20 simplifies to 2 square root of 5. Then, from there, you'll notice that when I rewrite this, each term in the numerator and each term in the denominator can be divided by 2. So do it. That leaves you with a negative 1 plus or minus square root of 5 over 2. These are real zeros. So those are included in the answers that we got from the last page, which was negative 1, and this 0 right here, 5 over 2. So all of these are the real zeros. So for example, in this exercise, if we had gotten some kind of imaginary number here, then yep, we can stop. But since we didn't, we had to go through and simplify all the way down to the end. All right, last topic coming up. For this last example, not too bad. We're just going to go in the reverse order of everything that you've already seen in this video. We will be given some zeros, like 1, 0, and some imaginary ones, and an initial condition, which corresponds to a point of the graph of the function. And we want to create the function down here. And this is most of the function. We'll get to the other piece of the missing piece of this function in a moment. I think you can see pretty easily that the 1 with multiplicity 2 corresponds to this factor here. Let me outline that in red. So the 1 multiplicity 2, if you have x equals 1 and you get a 0 on one side of the equation, subtracting 1 from both sides, you'll get the factor, and the multiplicity is 2, which means the exponent is 2. The next one here, the 0 multiplicity 3, there we go, corresponds to this factor. If you have a 0, 0, then the factor for that would be x, right? X equals 0. You need a 0 on one side, the other side will be the factor, boom. It's these other two zeros that I want to address, the imaginary zeros. And a few examples ago, when the answers were plus or minus I squared root of 3, I said, hey, imaginary zeros come in pairs. This is where that is important. So the imaginary zeros that you'll see may only be giving you half of the story. What do I mean by that? Well, with the imaginary zeros, we have 3i and 1 minus I. And when I say half of the story, imaginary zeros always come in plus or minus pairs, but only the imaginary part is what is plus or minus. So you can see with the 3i, it's a positive 3i. The other 0 that corresponds with this would be a negative 3i. With the I minus 1, that is one of the zeros in the pair. The other 0 for the imaginary pair would be 1 plus I. Right? Only the imaginary term, it has opposite sign, minus plus. Cool. So with that now, we can start writing out, what would we have? X minus 3i times x plus 3i. And that would correspond to this one, because you'd have to subtract 3i and then add 3i to both sides of this equation that we've started way back over here. And for these other two, let's just do the I minus 1. We know x equals, 1 minus I. If you get a 0 on one side, that would look like x minus 1 plus I would equal 0. So if you have an imaginary 0 that has two terms, you need to take the opposite sign of both terms, and that is how you create your factor. So the two factors here would be, let's see, x minus 1 plus I and x minus 1 minus I. Now comes the matter of multiplying all this stuff together. When I say all this stuff together, you only want to multiply the factors of the pairs of the pairs of imaginary zeros. So I don't want to be multiplying this x plus 3i times x minus 1 plus I. I want to stay only with the plus and minus pairs. So the positive 3i factor will be multiplied to the negative 3i factor, and the I minus 1, 1 minus I and 1 plus I factors will be multiplied. And that's it. How do you do that? Well, it's pretty simple. We just distribute like you normally would. With the first two here, x times x is x squared, x times positive 3i is positive 3xi. So x squared, positive 3xi. Then you distribute the second term. So I've got negative 3ix, which I can rearrange to be negative 3xi. And then negative 3i times positive 3i is negative 9i squared. Cool. Some nice things happen here. These two terms in the middle reduce away, and you're left with x squared minus 9i squared. The problem here is there's still an I in our expression here, in our factor. You can't have I. So I'm not going to write this down, but please write it down yourself. I squared is equal to negative 1. So whenever I have an I squared, I think of it as a negative 1. So when I look at this now, I'm thinking x squared minus 9 times negative 1. Well, negative 9 times negative 1 is a positive 9. This is x squared plus 9. And you can see where that factor comes from right down here. As for this other set of factors that you need to multiply together, it gets a little more involved, and that's because you're multiplying two trinomials instead of two binomials, but the idea is the same. You take each term in the first polynomial, so x times x times negative 1, x times negative I. So that's x squared minus x xi. And then you keep going. You worked with the negative 1 next and multiply it to everything in the second polynomial. So there's a negative x. Let's see. Negative 1 times negative 1 is a positive 1. Negative 1 times negative I is a positive I. And then I multiply the positive I here to everything in the second polynomial. So I times x is positive xi. There we go, positive xi. I times negative 1 is negative I. And positive I times negative I is negative I squared. Cool. So lots of things reduce away here. We've got these plus or minus xi's that reduce away. There we go. We've got these plus or minus i's that reduce away. And you can see that we're left with something that looks like, I don't know, what is that? X squared minus 2x's plus 1 minus I squared. But again, the I squared is equal to -1. So here you are subtracting a -1, which is adding 1. And so subtracting a -1 is adding, 1 plus 1 is 2. Let me fix this sign here. Go. So I goofed on the sign down there at the bottom. So that's how you get this factor here. As for the initial condition, I will have to take care of that for the next slide. About this initial condition, when you find a function solely based on the zeros, let me just draw a quick picture here. You'll notice that if you only have this 0, and this 0, there are lots of different ways you can draw a function going about those zeros. You can draw something that looks like this. You can draw something that is a little bit more stretched out, like this. You can draw maybe something that got reflected and is a little bit squished, like this. So there are lots of different ways that this can happen. What this initial condition is doing here is trying to figure out which a value should you give this function. So we're looking for a. And before I go any further, I did change this to a -1 from the last slide. Otherwise, it wasn't going to work out at all. So changed it to a -1. How do we figure out what this a value is, this leading coefficient? Well, the only thing that we have to do is substitute, just like it is up here, substitute -1 in for all the x's. And then when we do that, we can set the entire expression equal to 20. Because that's what you should get. You should be getting 20 when you substitute -1 in for all the x's. So it'll look like this. There you go. Substitute -1 in for all the x's. 1, 2, 3, 4, 5 times. Set that entire function equal to 20, and now we can solve for a. A is the only variable that's left over. So let's go through and simplify each factor to see what that gives us. -1 to the third power is -1. -1 minus -1 is -2. -2 squared is 4. So this one is a 4. We have -1 squared, which is 1. 1 plus 9 is 10. And this last one here, we have -1 squared, which is 1. -2 times -1 is 2. 1 plus 2 plus 2 is 5, equals 20. So this is our equation now. A times -1 times 4 times 10 times 5 equals 20. The easiest thing for you to do is to, I think, simplify all of this stuff here, multiply all these numbers together. You're going to end up with -200 a equals 20. Solve for a, divide by -200. You have a equals 20 over -200. Divide top and bottom by 20, -1/10. So your final answer here, yes, we're finally there. The final answer here is the function with this value substituted in for a, or at the beginning of everything, and then all of the x's here, x cubed, all of your factors that you found from the previous bit of work. All right, that does it. I hope this makes sense for everyone out there. And I wish all of you the best of luck.